And so let's do some recall here. So recall that for an alternating series that looks like such, that converges, we know that the sum of that series minus the partial sum to some value, to some term number n, will be less than the next term in the sequence. Okay? Which means that the difference, the error between the infinite sum of the series S and the partial sum S of n is less than or equal to the absolute value of the an plus 1 term of the series. In other words, the error of the partial sum is bounded by the first unused term. Okay, so we learned that back in the alternating series. This is fine if we have an alternating series, but what about other series that are not alternating? So that's the big question. Is there a method we can use so that we can guarantee that our approximation of a series, no matter how many terms we use, is going to be within a set amount of the true function? Okay, so that's what we're looking at. That's our question. And so this is where the Lagrange error bound came in. So I'm going to go ahead and lay this out for you so you can kind of start seeing it. Taylor, for our Taylor polynomial, let f be a function that has n plus 1 derivatives in an interval containing c and x. There exists a value z between x and c such that the function is the Taylor polynomial. This right here is the error between the Taylor polynomial and the true function, and this is equal to this quantity right here. The n plus 1th derivative of that z value, n plus 1 factorial x minus c to the n plus 1. This says that there is a number between the center value and some x that you are approximating, that if you plug it into the next term of the Taylor polynomial, you will get the exact difference between your Taylor polynomial and the true function, if we can find that value z. Okay, there's some number in there that's going to be the exact value. Okay, so that's where we get this down here. The difference between the Taylor polynomial and the original function, okay, is equal to that error, that remainder, okay, and that is going to be less than or equal to the maximum value of that derivative at some value z. Okay, now z is going to be all the numbers that are in there. Okay, and if you find the exact one, the one that exactly matches, then it will be the equal part of it. Otherwise, all the rest of them will be bigger than what you need it to be. And so that's where this comes in. The max value of the n plus 1th derivative at every z value between c and x, that's what that is right there. The center and the value that we are approximating f at. Because we can't find the one value of z that will get us the actual difference, the error between our Taylor polynomial and f of x, we find the maximum possible derivative for all the z's in there, and then we know that our error is no more than that. And so we have bounded it at that point. Okay? So that's the concept behind it. Here's some keys to the Lagrange error bound that we want to look at. We are not finding the actual error. We are only bounding it. We're trying to find the most it could be. So we know that we're bigger than, we're always going to be less than or equal to that. We still use the first unused term of the Taylor series for the function to find the error between the function and the Taylor polynomial. We often overestimate the error bound since we can rarely find the value of this. Okay, very difficult to find this value. So we always overestimate, and we will find the value of this in one of three ways generally. Okay, so how do I find this max value of this n plus 1 derivative at the z's in there? Okay, so here's the methodologies that's most likely going to occur. The first one here, that's blurry, give me a second here. Well, not much better. We will find the value of this in one of three ways. You're going to be given a graph, okay, of y of this, and so then we can see clearly a bound for the interval. F of x is a sine or cosine function, And the max of a sine or cosine function is 1, so that's one way they'll do it, so that you have to use the 1 for a sine or cosine function. And we are told the max value. This can be directly or indirectly. So somehow you're going to be told its value. Okay? So those are the three methodologies that you're most likely to occur on the AP exam. So I have an example here we're going to do. Let's take a look at it. So we want to approximate f of x equals the cosine of x at x equals 0.7 using the third degree Taylor polynomial centered at c equals pi over 3. What is the upper bound of the error of this approximation? Okay, so we're going to go through that process there and we're going to see if we can figure it out. So the first thing I have to do, since we want a third degree Taylor polynomial, is take this function, because we know we're going to need the next one past the third degree, so we need 4 derivatives, the fourth derivative of this function. So we're going to go over here and we're going to find them all. So here's f of x is the cosine of x. F prime of x is negative sine of x. F double prime of x, negative cosine of x. F triple prime of x is sine of x. And the fourth derivative of x is going to be the cosine of x, back to where we were. We want to evaluate all of those at our point. So what is the cosine of pi over 3? We get 1/2. And over here we're going to do a negative sine of pi over 3. And negative 2. So this right here is, I'm not going to write it all out, I'm going to write it this way now. This is the second derivative at pi over 3. And then we're going to do the third derivative at pi over 3. And then we're going to do the fourth derivative at pi over 3. And get these values in here. So this one's going to be negative 1/2. This one should be the square root of 3 over 2. And this one down here should be positive 1/2. Okay? Let's find our third degree Taylor polynomial. What do I know it to be? It's going to be the first term, so it's going to be 1/2, plus the first derivative, which I already have a value for, so it's going to be a negative root 3 over 2, times x minus the center, plus then the next number, which is going to be in the next derivative, which is negative 1/2. This is going to be over 2 factorial, x minus pi over 3 squared. And then we want to do one more, and this one's going to be the third derivative, x minus pi over 3 cubed over 3 factorial. So that's our Taylor polynomial. We can clean all that up and kind of make it look a little bit more pretty. And 1/2, this will be a negative root 3 over 2 x minus pi over 3. And this over here is going to be a negative 1/4. All this right here works out to be 1/4 x minus pi over 3 squared. And then this part over here, this right here is 3 times 2, so that's a 6. Times 2 is 12. So we're going to have a square root of 3 over 12. And then an x minus pi over 3 cubed. So there's our Taylor polynomial cleaned up just a little bit. And so then we want to find our value there at our point 0.7. So we're going to use this now to approximate that. I'm not going to plug it in, but you can plug it all in for these x's right in there and there. And when you do, you're going to get an approximation for this of 0.7645. Okay? So there's our Taylor approximation for that. What is the upper bound of the error of this approximation? So now I got to do that. Our error, the difference between, I'm writing out this formula here of our polynomial. So this is the formula, the frame you want to know is this which is equal to this. Remember, there's some value in between at z, okay? And this is n plus 1 factorial. This is x minus c to the n plus 1. There's a value that's exact. That's why I have an equals here. But that, since I can't find that exactly, I'm going to find the maximum it can be, and that's where this comes in. This is why it looks similar. N plus 1 of z. This is still n plus 1 factorial, and this is, they put it in absolute values, so I'll put it in absolute values for you. So that's why we have this. Okay, now it's less than, because that we're either going to be given or we have to determine what it's going to be in some fashion. Because our function has a cosine in it, it's going to use that second process where I give you a function as a sine or a cosine. So that means the max is going to be represented by a 1. Okay? Because the derivatives, no matter what it is either going to be a sine or a cosine. And so the absolute value of that's going to be 1, and that's what we're going to state right here. So since the nth derivative of x is either plus or minus the sine or plus or minus the cosine, we know that this derivative of some z is always going to be less than or equal to 1. Okay, which means our max of that is going to equal 1. The biggest one it can possibly be. Okay, so with that, I'm going to try and put that in there. I might have to jump over here to another piece of paper, it looks like. I didn't give myself just enough room. So I'm going to write it right here on this paper right here, and you can kind of like, and I'll show you the final version of it. So here's what you're going to write. This is all the reasoning behind it, so you understand what's going on. And so here's what you could write once you understand what's going on. You go right to this right here. This is what you would write on the AP exam. Okay, this right here is less than or equal to the max of this, the fourth degree of a z. This is going to be over 4 factorial. This is going to be 0.7 minus pi over 3 to the 4th power, and that's going to be 1. And then you have all this again. 1 times 0.7 minus pi over 3 to the 4th power over 4 factorial. So that's where that number comes from. That's how that works. And so then you can approximate this out on your calculator, and you should get this right here. Okay, so that's the reasoning behind everything for the Lagrange error bound. All right, so let's take a look at another example. And I have that one right there. Okay, approximate this. Now this is a natural log at x equals 2.2 using a third degree Taylor polynomial centered around c. What is the upper bound of the error of this approximation? So basically the same question again. We're just going to do it with a different function and see how that lays out. Okay, so same thing again. You have to find all your derivatives. So we have the natural log is our function. Okay, and then from that we're also going to find the value of this at our point 2. So then the first derivative is 1 over x. This will equal 1/2. And the third derivative, second derivative is going to be a negative 1 over x squared. So our second derivative at 2 is going to be a negative 1/4. Our third derivative is 2 over x to the third. So at 2 is 1/4. And then our fourth derivative is a negative 6 over x to the fourth. So our fourth derivative at 2 is a negative 3/8. Okay. Get in the habit, I recommend highly when you're doing a Taylor polynomial, that you write it out without simplifying it out. Just plug in the players. Don't try and simplify it at the same time. This will be plus, and then I'm going to plug in -1/4. This will be x minus 2 squared over 2 factorial, and then this will be 1/4 x minus 2 cubed over 3 factorial. So plug it in first and then simplify it out. I think it's it helps you with any errors that you might make and things like that. That's a plus. This will be minus. I'm sorry, this is a 2 on the bottom, so this will make an 8. And then this one over here is going to be 6 and 4, that's 24, so 1 over 24, x minus 2 cubed. And then you're going to plug in, excuse me, that's a p, 2.2. And when you do, you should get this number right here. Okay? All right, so the next part, that's our Taylor polynomial approximation right there. We want to find out how the error of this. And so we want to plug in our numbers. And so here we go. F of 2.2 minus P3 at 2.2, okay, is going to be, that is equal to that remainder, which is equal to the fourth derivative of some z times 2.2 minus 2 to the fourth over 4 factorial, the absolute value of that. But that is less than or equal to the max of that. Since I can't find that, what's the max of that? Of z. And this is going to be 2.2 minus 2 to the fourth power over 4 factorial. Okay? And so from this natural log and the way that lays out, okay, we know and that for z in this interval 2.2, use the endpoints of the interval, okay, to find the max. Okay, and so we can do that, and we know that the fourth derivative of x, we already have it above, is a -6 over x to the fourth. And so what is the fourth derivative at 2? And you're going to get a -6 over 2 to the fourth, which is a -0.375. And what is the fourth derivative at 2.2? And you get -6 over 2.2 to the fourth power, which is a -0.256. Okay, so which one has the larger absolute value number? Not based off of the sign, but based off of the absolute value of it, so that's this right there. Okay, so we're going to use that number right there. Okay, this is what we're going to be using, and for the max. And so our R of 3, which is this thing, we should write it like that. So F of 2.2 minus P3 of 2.2 is going to be less than or equal to the absolute value of -0.375 minus this, 2.2 minus 2 to the fourth power, all over 4 factorial, and that gives us this error. And there you go. Okay? So that's that example right there. Okay? And I'm going to show you another one instead of working it out, I'm just going to go ahead and show it to you, the final version of it, so you can kind of see how it lays out. Okay, so here in this example right here, you were given a picture of the absolute value of the fourth derivative. Okay, and so we know that our error is going to be less than this quantity right here. This would be the maximum value of the graph between 1/2 and 1, because I'm looking in here. So between 1/2 and 1, what is the maximum? Well, I don't really even know what that is, but I know that it's always less than 30. So this graph is less than 30, so I can use that number as the maximum right there, since I don't even know how to find that value. So I pick a number that's everything's below, and that gives me this answer over here. So this is how I can use a graph to bound the upper part of that. And because I took a number bigger than that, okay, this value is less than whatever this would be. So make sure you do your signs properly. Okay? So there's that. Now I'll let you pause and copy that down if you need to. All right? And so that concludes the Lagrange error bound. If you have any questions, just let me know in class.